Hello everyone, my name is Shada Melis Turkarman. I am a master's degree student of computer engineering at Yashar University. Today, we will talk about the team formation problem and existing studies focusing on it. Before I begin, I would like to thank you all for your understanding about my way of presenting arising from my speech disorder. Let's start. We will start with the necessity of teaming. Then, we will take a look at earlier studies on the team formation problem, shortly TFP. Although there is no exact formulation of TFP, we will examine into a basic formulation and its computational complexity class. Before we dive into proposed models for solving TFP, it will be worthwhile to explore some heuristic and meta-heuristic methods briefly. Finally, we will summarize all and finish the presentation. As the day goes on, basic tasks yield to more complicated ones in almost all sectors and industries. This increasing complexity leads people to work in teams, since the teams perform better than individuals, especially when multiple skills and perception are required. Teaming plays a significant role in success, not only in business, but also in education of both students and employees. Within a team, the knowledge and skills are also diverse, beside the information and other resources. When two or more people share information and take decisions, it can be assumed as a teamwork. However, huddling people together cannot guarantee that they will work productively and take proper decisions. Under these circumstances, a problem called the team formation problem started to take part in the literature. As its name indicates, the team formation problem is to come up with an efficient allocation of resources to a group in a way that the required skills and an optimal level of cohesion are fulfilled. This can be an allocation of the developers to the projects, or taxi drivers to competitive groups, or students to working groups in a classroom. There are various research examining the importance of team formation and its effects on the performance and productivity. According to one of these studies, it is stated that the trust between project team members in inter-organizational projects promotes product innovation. Baden and Price list some of the impacts on the success of the team. These are the interdependence of group skills, integration, trust, and the technical skills of each team member. It is clear that the social interactions between team members has to be considered during the team formation. Now, let's take a look at some of earlier studies on the team formation. The first computational study on the team formation problem, which takes the presence of a social network of individuals into consideration, was by Lapaz, Liu, and Terzi in 2009. They have tried to maximize social cohesion while grouping the people with different skills. Their model made use of the graph structure. We will talk about their problem formulation later. Li and Shan have extended Lapaz and his friend's algorithm. They generalized the team formation problem by associating each required skill with a specific number of experts. The proposed method condenses the expertise information to the team graph according to required skills. They have developed a density-based measure to improve the effectiveness of the team. In 2011, Farhadi and his friends proposed a model for forming an effective expert group in a social network by using of skill levels of team members and the minimum communication cost. In their next study, they took the set of skilled expert groups that are strongly correlated based on both their skills and the best connection among them. Then, they aggregated the graph of experts to the set of strongly correlated, skilled expert groups. In this way, the search space is significantly reduced, and the growth of redundant communication costs is prevented. So the effectiveness and efficiency of formed teams are increased. In the same years, Karger and Ann introduced the problem of finding a team of experts with a leader, which is responsible for monitoring and coordinating the project. Thus, a different communication cost function was required. They defined a new communication cost basis on a function considering communication costs between each pair of experts and a function considering the costs between a leader and each of the experts in the team. Via this study, they propose two procedures that produce top K teams of experts with or without a leader. In recent years, the team formation problem has been studied by focusing on the different dynamics of teams. For instance, Fathian and his friends proposed a team-forming model according to expert skills, experts' collaboration network, and experts' reliability. Their model forms a team and a backup for each member, which is likely to leave the project. Another study belongs to Perez, Cruz, and Diego. They introduced a procedure to select a set of individuals who should be chosen from a given pool of resources and to combine them into one or several simultaneous groups. Of course, by assuring the maximum possible overall work efficiency with regard to the social interaction. As a weak point, their procedure tended to depend on manual computations. Later, Gutierrez and his friends presented a problem called Multiple Team Formation Problem, shortly MTFP, which aims to form not a single team, but several teams. In their study, 3 algorithms are proposed for the solution of MTFP. They tried to allocate people with single skill to projects by considering fractions of people's dedication and the preferences of people about potential teammates. I will talk about the details of this study a bit later. In each study, the team formation problem is formulated with minor distinctions. As we mentioned before, Lapaz, Liu, and Terzi have studied the team formation problem, considering not only the skills of experts, but also the social cohesion among them. It will be nice to talk about their problem definition briefly. Assume that there is a pool of n individuals, call it C, and a universe set of m skills, call it S. A subset of the individuals, say C', possesses the skill S sub j if there exists at least one individual in C' that has S sub j. A task, T, is defined as a set of required skills to perform a job. In other words, T is a subset of S. So that, if S sub j is an element of T, this skill is required by task T. The set of skills that are required by T, and for which there exists at least one individual in C' containing them, is the cover of a set of individual C' with respect to task T. The cover is denoted by capital C. Lappas and his friends fundamentally benefit from the graph structure and the pre-existing graph algorithms for the social cohesion. Individuals are organized in a connected, undirected, weighted graph G. In this graph, each node is an individual in C, and each pair of individuals is connected with an edge in E. Each edge is weighted directly proportional to the communication cost between the nodes it connects. The distance between the nodes I and I' is the sum of weights on the shortest path from I to I'. The team formation problem is defined as, given the set of n individual C, a graph G, and task T, find the Z' which is a subset of C, so that the cover of a set of individual C' with respect to task T is exactly T, and the communication cost is minimized. In the study of Lappas and his friends, two instantiations of the communication cost function are focused on diameter and minimum spanning tree. In the diameter function, the communication cost of C' for a given graph G is the largest shortest path between any two nodes in the graph. Or, let's say, the longest way with the smallest sum of weights is the communication cost. In the minimum spanning tree function, the communication cost of C' is the sum of the weights of the minimum spanning tree's edges. I hope that this sample formulation helped you to imagine the TFP better. Let's talk about the computational complexity of TFP briefly. In computer science, one way of classifying the problems is to classify them according to their computational complexity. NP hard problems, you can see in the schema, have a high complexity. They are impossible to be solved in an acceptable time when the problem size increases. Lappas and his friends proved that the team formation problem is an NP hard problem. Intuitively, it is even more complex when multiple teams are formed for multiple tasks. For such problems, I mean NP, and harder problems, heuristic and meta-heuristic approaches are much more powerful than the exact methods to find an optimal solution in a shorter computation time. Before we dive into the proposed models for TFP or MTFP, it will be worthwhile to touch briefly on some heuristic and meta-heuristic methods. Generally, local search heuristics are used in optimization problems, and they are combined with some other heuristic and meta-heuristic approaches. The space of candidate solutions is called search space. Local search algorithms travel from solution to solution in the search space by using a neighborhood function until it finds a solution considered optimal or a time bound is elapsed. Variable neighborhood search, shortly VNS, is a meta-heuristic for solving combinatorial and global optimization problems. Actually, it is a kind of local search with a guided change of neighborhood in the search process. VNS does not follow a route, but it investigates increasingly distant neighborhoods of the current solution and jumps from a solution to another one if and only if an improvement has been detected. Genetic algorithm, or shortly GA, is a population-based evolutionary algorithm. The algorithm originates from Charles Darwin's theory of natural selection. Each candidate solution of a problem is called chromosome or individual. A set of candidate solutions, namely individuals, are created in the initialization phase, and new generations are produced by following the steps shown in the schema. Here, local search is optional. As we said before, the local search can be combined with some other heuristic approaches, like with the GA here. A deterministic crowding evolutionary algorithm is basically a genetic algorithm using a deterministic crowding approach. In this approach, similar pairs of individuals are recombined, and a pair of children must have a better fitness value than its parents to survive. The inspiration of swarm intelligence often comes from nature, especially from the biological systems. Particle swarm optimization, shortly PSO, algorithm, is one of the swarm intelligence algorithms. In the current slide, we see a simulation of particle swarm optimization algorithm over a search space. In PSO, the optimization is done by a population of candidate solutions, namely particles. These particles move around in the search space according to simple mathematical formulae over the particle's position and velocity. African buffalo optimization is another swarm intelligence metaheuristic algorithm that is derived from behaviors of the African buffaloes, which are a species of wild cows living in the African forests and savannas. The last algorithm is the Jaya algorithm, which is another population-based metaheuristic algorithm. It can be used for both constrained and unconstrained optimization problems. In Jaya algorithm, the solution obtained for a given problem should move towards the best solution and should avoid from the worst solution. Also, the algorithm requires only the common control parameters and does not require any algorithm-specific control parameters. Now, let's go over the studies combining these heuristics and metaheuristics with the team formation problem. Gutierrez and his friends formulated the multiple team formation problem as an optimization problem with a quadratic objective function, linear constraints, and integer variables. They tried to solve the problem by three algorithms: a constrained programming approach provided by a commercial solver, a local search heuristic, and a variable neighborhood search metaheuristic. As we talked before, they tried to allocate people to projects by considering fractions of working time and the people's teammate preferences. Since the study was for the allocation of only single-skilled people, the MTFP could be decomposed into subproblems in which people with the same skill are allocated to the projects. This property of decomposition fits on the nature of the constrained programming. For the local search and variable neighborhood search, they used similar neighborhood functions. As the result of this study, it is stated that, although some improvements are needed for the large-scale problem instances, the algorithms achieved satisfactory results for the midi-size instances. Among three algorithms, VNS slightly outperforms the other two algorithms. Costa and his friends proposed an automated approach to allocate multiple developers into multiple teams, of course by maximizing the technical compatibility between them. They preferred a genetic algorithm to simultaneously build multiple teams due to its suitability for combinatorial optimization problems. The implemented genetic algorithm uses the data from tag-based profiles of projects and developers. Thereby, the subjectivity in profile creation is minimized, and the profile information grows dynamically as the projects vary. As a result of experiment done by using the genetic algorithm on 8 real-world projects, 16 developers and 4 projects managers, the tag-based profiles yield to form multiple teams with a high level of satisfaction that can guide the managers about team formation. In a study of Yanni and Amandi, this time, the task is allocating the students to several teams in a collaborative learning context. There are 9 predefined roles like implementer, coordinator, resource investigator, and so on. Teams are formed according to the student's preference level for each of these roles. A deterministic crowding evolutionary algorithm is proposed for this multiple team formation problem. Via the crowding approach, the diversity in the population is preserved, and premature convergence to local optima is prevented. Based on the experiment done with 10 datasets having different complexities, the performance of the proposed model is compared with those of the exhaustive and random methods. It is stated that the proposed deterministic crowding evolutionary algorithm could achieve good solutions in an acceptable computation time. Last 2 studies that we are going to talk about belongs to Elishmawi and her friends. In their first study, they proposed a particle swarm optimization algorithm, but with a modification. They used the modified PSO model for allocation of the experts with multiple skills to a single team. The improvement in PSO is based on the newly introduced swap operator that is used at the particle's velocity update phase. Standard swap operator selects 2 experts and interchanges them. So, the swap operator takes 2 parameters, these are both experts. The new swap operator takes the desired skill into consideration. The experts with a particular skill are selected and swapped. That's why new swap operator takes 3 parameters instead of 2. For a skill S, it swaps expert I and expert J, where both experts have the skill S. This new PSO is called an improved particle optimization with new swap operator. The classical PSO and their new model are tested on the same dataset of different-sized problem instances. Although the deviations in classical PSO model are slightly smaller, the new model obtained less communication cost for formed teams. In their later work, they used Jaya algorithm with their new swap operator to accelerate the search process. They explained the reasons of selecting Jaya. Firstly, the Jaya algorithm has proved its efficiency in the economic optimization problems, especially elitist Jaya algorithm. Second reason is that it can be used in combination with other methods in identification and detection problems. Also, there is a proposed multi-objective Jaya algorithm for solving multi-objective optimization models. They claim that no research paper before considered the Jaya algorithm in social life, such as the team formation problem, as one of the discrete optimization problems. They tested their improved Jaya algorithm with a modified swap operator on 2 real-life dataset and compared against 4 metaheuristic algorithms. These are genetic algorithm, particle swarm optimization algorithm, African buffalo optimization algorithm, and standard Jaya algorithm. The results show that Jaya algorithm with a modified swap operator was faster than the other algorithms. Let me sum everything up and finish my talk. Today, we have complicated tasks in almost all sectors, including engineering, education, healthcare, and even transportation. For these complicated tasks, teaming plays a significant role in success. Thus, allocating people to the teams with a high cohesion has been a topic taking part in literature. It has been named team formation or multiple team formation problem. Starting from 2009, several studies have done on the team formation, considering the social network of people. We have talked about them in the first half of the presentation. Lapas and his friends proved that the team formation problem is an NP-hard problem. Intuitively, it is even more complex when multiple teams are formed for multiple tasks. For such hard problems, heuristic and metaheuristic approaches are much more powerful than the exact methods. For TFP, or multiple TFP, several models are proposed, such as constraint programming approach, local search heuristic, variable neighborhood search metaheuristic, genetic algorithm with and without deterministic crowding approach, swarm intelligence algorithms, standard and modified Jaya algorithm. Before ending the presentation, let me add a few things. To define the scope of a team formation problem, there are numerous factors that should be decided. Like, will we focus on single or multiple projects? Will each person have a single or multiple skill? Will the skillfulness level of people be considered? Will the teams have a leader or not? Will part-time allocation be possible? Will the team or teams be dependent on social cohesion, and so on? In the future works parts of the existing studies mainly indicate that a different heuristic or metaheuristic algorithm can be implemented. One or more internal steps of the proposed and tested heuristic algorithm can be improved. Scope of the defined TFP can be extended. For example, another combination of the factors can be chosen. The way of collecting data about social preferences of people can be improved. That's all I want to tell about the team formation problem and the existing studies. I would like to thank you all for being with me today.